Welcome to this video podcast on uniform circular motion. Now, uniform circular motion is a different kind of two-dimensional motion. You'll notice that I have a circle drawn here, and this would be if we had an object that was moving in both the x and the y directions, but was traveling in a circle. So this could be something like a yo-yo attached to a string as it goes around a circle. It could be a race car going around a perfectly circular track, although there are no circular tracks that I know of. Or anything at all that's going around in a circular path, Ferris wheel, something like that. As we have our object go around in our circular motion, we notice that there's two things. First, we have the word circular, which implies that we are going around in a circle. And we also have this word uniform, which is important for us to understand. What that means is that the magnitude of our velocity is constant. Now, what does that mean that the magnitude of our velocity is constant? Well, remember, magnitude of velocity is the speed. So the instantaneous magnitude of an object's velocity is how fast it's going, regardless of the direction. So if I had a velocity of, for instance, 5 meters per second at an angle of 30 degrees, the 5 meters per second, that would be my magnitude of velocity. So what we're saying is that this object, as it travels around in its circular path, is always going the same speed, no matter where it is. If we're over here on the side, it's going the same speed as it is here. It's going the same speed as it is here. It's like we set the cruise control on the object, and it's continuing on in its circular path. Now, if we think about what is happening with this object as it travels around in its path, let's say that our object is traveling in a counterclockwise path. So it's traveling this way around. So this is the object's path. If we can imagine at 4 different points what's happening with the velocity, we would see that at the side here, if it's traveling counterclockwise, its velocity would be going up this way. We would see the same thing, or I guess a similar thing, if we were here. Our velocity would be going that way. Here, our velocity is going this way. Here, our velocity is going this way. We've got a velocity here going this way, a velocity here going this way. Anywhere we go, we can draw the velocity. And so what that means is that we can identify the velocity direction as always tangent to the circle. It's always tangent to the circle. That means if we were to draw the velocity, it would create a line that hits the circle just at that one point. You'll notice here, this velocity, if it continues, it never goes on in the circle. Now, there's a couple of really interesting things. If we remember Newton's first law, this says an object in motion will stay in motion unless acted upon by an outside force. Or, another way to say that is, if the net force is balanced, our object is in equilibrium. If we had a yo-yo, for instance, and it was traveling around in a circular path, and I got to this point right here, actually, let's bring it to this point right here, and it gets to this point here, and then all of a sudden, I bring in a pair of scissors right here, and I cut that string. Newton's third law, or first law, the law of inertia, says that because this is the velocity at this location here, what's it going to do? Well, it's going to continue along in that path, and it will go this way. It will keep going this way once that cord is cut. It's a very important concept for us to keep in mind for later on. We should remember a couple of things about circles. The first is that if we have a circle of radius r, so that means that this distance here from the center to the outside edge is radius r, the circumference of that circle is then 2 pi r, or it's pi times our diameter. That's another way of looking at it. And we should also remember that the speed of an object in general is how far it goes in how much time. Speed is distance over time. Now, I mentioned that the magnitude of the speed is constant as we go around in this circle. But the question is, how do we figure out how much that magnitude of speed or velocity is? Well, we need to, in order to understand how fast it's going, we need to define the time it takes to go around the circular path. Because if we know that our speed is equal to our distance over time, we know that there is a set distance of 2 pi r every time it goes around the circle. So rather than having to get out our little ticker or tape measure and measure exactly how much distance it travels from here all the way up here and then divide it by the time it takes, we can just measure this radius here and take the value of our radius and multiply it by 2 pi and get the total distance that it travels along the outside of this path, this red squiggly area here. Right? And so if we then know how long it takes for that object to go around the circle, we can figure out how fast it's going, because we know that distance divided by time is the speed. So we have a special term for this, the time it takes to go around the circular path. Its symbol is a capital T, and that capital T is called the period. So I guess I'll use a colon here. So T is the period of rotation. So T is the period of rotation. And so then we can see our speed up here, which is distance over time. We know that going around the circle once, we travel a distance of 2 pi r, and the time it takes us to go around that circle is capital T. So that means that the magnitude of velocity for an object undergoing uniform circular motion is 2 pi r divided by t. And that's a really important equation for us to understand. I mean, it's not terribly important that we understand the equation. It's important that we are able to get back to this equation because we see its distance over time. Now, there's another term that we will use quite often, and it's this idea of frequency. And frequency's symbol is a capital F, and frequency is measured in units called hertz, or Hz. That's the symbol for it, Hz. It is spelled H-E-R-T-Z. And frequency is kind of the oftenness of something. It's how often it completes a period. It's how often it completes one full circular path. And so if we can imagine our object going around a circle, if we can imagine our object going around a circle, and let's say it takes 2 seconds for it to go around the circle, that means that our period is 2 seconds. And so then our frequency is measured as how many periods it goes every 1 second. Well, we know if it takes 2 seconds to go around once, our frequency then is 1/2, because every 1 second, if our period is 2 seconds, every 1 second we will go around half of a revolution. So that's 1/2, or 1/2 hertz. Now, the same thing would happen, right, if this was 3 seconds. Then that would mean every 1 second we would go around 1/3 of our rotation. And if it was 4 seconds, it would go around 1/4. And so the relationship between frequency and period is very simple. They are inverses of each other. Frequency is 1/period, and period is 1/frequency. So they are complete inverses of each other. Now, if we have an object going around in a circular path, the other really important thing that we need to understand is the direction of our acceleration. And so let's imagine again that we're still going around this way. Our velocity vector is pointed then right here, and right here, and right here, and right here. And so when we take a look at that, in order for this to happen, we know that we must have an acceleration vector that pulls us in some direction. Okay? Now, the length of this vector here, we'll call it L, is the same as the length of this vector here, is the same as the length of this vector here, is the same as the length of this vector here. And when we look at this, that means that when we add an acceleration to this velocity here, we cannot increase or decrease the length of that resultant vector. So if you would imagine, if we had a velocity vector that went this way, and we added to it an acceleration vector that went this way, right, and we have to actually add to it an acceleration times time vector because that's our delta v vector, the result is a longer velocity vector. So if this is our v initial vector, and we add to it a blue acceleration times time vector equal to delta v, we end up with a v final that's longer than it was before. The same thing happens if we flip around this. If we flip this around like this, we end up with a final velocity vector that's actually shorter than before. And when we look at it, the only way that we can add a blue acceleration times time vector to our velocity and not change the length of it is if we add that perpendicularly. So if you can imagine, if we have an acceleration vector that pulls directly this way, a, and it acts for some amount of time t, we can add that infinitely small acceleration vector that's not going to change the length of our velocity vector. It's just going to tug it ever so slightly this way. Now, if that acceleration vector acts for any amount of time, all bets are off and we end up with an object whose velocity is increasing or decreasing. So, but if we add just a tiny, tiny, almost kick or flick, we end up with a final velocity vector that has just changed its direction. So this v final green vector. And so the result of this is that at every single point along this object's path, it is accelerating in toward the center of our circle. Because our acceleration vector can only change the direction and not the length of our vector, we must have an acceleration that points directly toward the center. So for uniform circular motion, we know two things. First, we know that the velocity vector points tangent to our circle. Second, we know that our acceleration vector points toward the center. And the result is that we have a new name for this type of acceleration vector. It is called centripetal acceleration. And that's what we're going to focus next video on, this idea of centripetal acceleration, an acceleration that pulls directly toward the center of our circle. Okay, so let's try just one practice problem here. Let's say that we have an object that is traveling around in a circle, and let's just say that this is a race car that's traveling around in some magical circular path. And that circular path has a radius of 500 meters. So it's a pretty big circular path. So 500 meters is the radius of this. And let's say that we know that this object travels 1/3 of a lap every 25 minutes. Let's just call it 25 seconds. Okay, every 25 seconds, this object travels 1/3 of a lap. And the question then is, how much is the magnitude of its velocity? How much is its period? That is, how long is it going to take to travel around once? And draw at least 4 velocity vectors and 4 acceleration vectors. Okay. So go ahead and try to do this. Pause the video and then come back. And welcome back. So the first thing, the easiest thing for us to do probably is to look at this idea that we go 1/3 of a lap every 25 seconds, which means that we will do 1 lap in 75 seconds. Okay, so 1 lap in 75 seconds means that our period is equal to 75 seconds. 75 seconds. Okay, now, I would also likely ask you for the frequency of this thing, and the frequency of this is going to be 1 over our period, which is 1 over 75 hertz. So that's a good thing to keep in mind. Now, the next thing for us to do is to find the velocity, because we know that in general, our velocity is given by 2 pi r divided by t. So this is going to be 2 pi times 500, and we're dividing that by our time period of 75 seconds. So when we do that, we end up with a velocity of 41, not 71, 41.8 meters per second. Okay, 41.8 meters per second. Now, to draw our velocity vectors, we can pick, there's 4 locations that are easiest to pick. Those are the locations where we are going up, down, left, and right. Now, I realize I didn't tell you what direction it was traveling, so let's assume that it's going to be traveling clockwise around this. And so, as a result of it traveling clockwise, that means that at our easternmost location, the velocity vector points straight down. At our southernmost location, the velocity vector points due west, or directly to the left. At our westernmost location, our velocity is pointing up, and at our northernmost location, our velocity is pointing to the right. Similarly, our acceleration, remember, is just going to be in toward the center. So our acceleration vector will be here, our acceleration vector will be here, our acceleration vector will be here, and our acceleration vector will be here. Now, a couple of things to remember. When we're drawing these, we should somehow show that the magnitude of our velocity vector is constant. And we can do that by just applying a small hash mark like this. Our velocity vectors are all the same. Therefore, then even if you don't draw them exactly correctly, you still get a good picture. The same thing is actually true for our acceleration vectors. All of them are the same magnitude. And we'll get into that next video. That's all we've got for this video. Thanks for tuning in. See you in class.